thank you very much. I'm Alberto Huertas, a postdoctoral researcher of the group. My main background is cybersecurity. So the idea of this talk, or my main idea with this talk, is to give you an overview of three of the research lines in which I'm collaborating with some researchers from other organizations and universities. The first topic that I would like to mention is the continuous authentication in the smartphones and personal computers. The second one is the detection and mitigation of ransomware in clinical environments. And the third one, also aligned with the next talk presented by Sergio and aligned with his PhD thesis, is the cybersecurity in brain-computer interfaces. So related to the first topic, the continuous authentication concept arose with the objective of improving the limitation of traditional authentication mechanisms. And basically, this kind of traditional authentication system, they are based on something that you remember or something that you have, like, for example, a password, a token, a PIN code, a pattern, and so on. And the main problem that they have is that they can be stolen or they can be forgotten. Another limitation of traditional system is that they just authenticate the user from time to time. For example, when we use our smartphone and we introduce our code or our pattern, we don't introduce the code until the device is locked and again unlocked. But what happened during the period that we are using the device? And the last problem, the last limitation is that they are intrusive systems, which means that you have to stop doing whatever you were doing and then introduce your credential, your authentication credential, and then go back to the thing that you were doing. So the idea behind the continuous authentication concept is that we monitor the behavior of the user when he or she interacts with his device, like, for example, a smartphone or a personal computer. And we monitor this interaction for a given period of time, normally 2-3 weeks, and we create a behavior profile. And once we have the profile, we normally use artificial intelligence. We train a model, and then in real time, basically, we compare or we evaluate how similar is the behavior of the person, the behavior of the device, compared to the well-known model that we have trained. This evaluation gives us a result, and if the result is higher than a threshold that we established, we can say that the owner or the person using the device is the owner, and if it's lower, it could be an attacker. So in this topic, I mean, our research work is focused on two different scenarios. The first one is focused on smartphones, and the second one is in personal computers. And talking about the smartphone scenario, as I was saying, we basically create profiles, and in this scenario, we create the profiles according to two different dimensions, like the application statistics and the sensor data. So we look at features or data, like, for example, the number of applications running in parallel, the number of applications that we have in our smartphone in background, the patterns that we have to change from one application to another, even also the position of the mobile and the inclination of the smartphone when we use it, the hand with which we use the device, the vibration when we type, and so on. So in terms of, this is for the smartphone scenario. For the personal computer, we also use the application statistics, but also mouse and keyboard data, like, for example, the movement that we do with the mouse, the clicks, the mistakes that we make when we type, how fast we type, and all this kind of data. So considering this dimension and this feature, we generate a profile, as I was commenting, and we evaluate in real time the profile. So here I want to show you a video, which is basically a prototype. We have created a couple of prototypes, one for the smartphone scenario and another for the personal computer. And here I just want to show you how our system, how our solution works in a real environment. We already, here in this video, we are going to see how the system is working in real time, which means that we already have trained the model that I was commenting, and then in real time we are evaluating the behavior of the person against the model, the well-known model. At the beginning of the video, we will see the owner interacting in his own way with the laptop, and later we will change the person interacting with the device, with the laptop, and we will see how the system is able to detect that, you know, the owner is not using the device, and it will be locked. So here we can see that different applications like a web browser, and you know, the user is using the trackpad, the mouse, the keyboard, different application to see the PDF, to write. Everything is, you know, here there is no restriction. Basically, the user is, you know, using the laptop in his own way. And every minute, our solution is running in background. Every minute is monitoring the behavior, and it's evaluating if this behavior is, you know, it's aligned with the behavior of the model, the well-known model. Now we have seen that we have changed the user, and now we are simulating that we have an attacker using the same applications, using the trackpad in his own way as well, and using the, you know, the keyboard and everything. And we will see now in the video like the system. Like the system is able to detect that the user interacting with the device is not the owner, and then the device will be locked. If we wait, yes. Here we will see. Yeah, he is writing now. Here we can see that the laptop has been locked, and which means that the system has detected that the user interacting with the device is not the owner. So basically, here we already have a prototype for the smartphone device, the prototype for the personal computer, and now we are working on the integration of both for an IoT scenario, you know, creating profiles belonging to different or multi-device profiles. Okay, so that's the current, the ongoing work that we have in this research line. So the second topic that I would like to mention in this talk is the detection and mitigation of ransomware in clinical environment. So ransomware basically is a kind of malware which infects a device, encrypts or ciphers the data, requests a ransom or requests some money to get back our data, and then spreads across the network to repeat the process and, you know, and cipher and encrypt other data belonging to different devices of the network. And nowadays, this is a real problem of the clinical sectors. Last year, in 2019, the 64% of medical organizations, hospitals, they reported some problem with this kind of ransomware. And ransomware right now is the 85% of the malware in the clinical environment. And we already have, you know, hospitals that they had to pay some money to get back their data. And the limitation right now in the state of the art is that current antivirus and, you know, intrusion detection system and firewalls, they are not able to detect new families of this kind of ransomware, because they are based on signatures, and signatures are based on, you know, on something that you already know, you know, existing malware or existing ransomware. So our idea here, our contribution, or our proposal is to monitor the behavior of the clinical network, which is basically a normal network with different clinical devices or medical devices, and also databases and so on. So the idea is to monitor the behavior of the communication of those devices, to create a fingerprint. And once we have the fingerprint, we train an artificial intelligence model, and then in real time we evaluate how similar is the behavior of the whole network compared to the model. In this approach, we were considering classification and anomaly detection to detect well-known ransomware, and also new families of ransomware. So once we detect the ransomware using the software-defined networking paradigm, we were able to to isolate the device, blocking the communications, and using the network function virtualization technique, we were able to replace the infected software. And very quickly, yes, the last point that I want to mention is the brain-computer interfaces. Sergio is going to talk more in detail in this area, but a brain-computer interface is a device which is able to connect our brain with external elements or external devices, and then in both ways. So when I say in both ways, I mean that we are able to record neural activity, but also we are able to stimulate and inhibit neural activity, or the activity of individual neurons. And here, basically, we are looking at the current vulnerabilities of existing, interfaces, and we are also proposing new cyber attacks to later detect and mitigate these kind of cyber attacks. So that's all from my side. Thank you very much for your attention, and if you have any question. Yeah, can you hear me?
Yeah, we can hear you. Does anyone have any questions?
Yeah, I have a question. Can you hear me?
Sure.
Yeah. Okay. So for the first one, the continuous authentication on smartphones and personal computers, I have two questions. One is when the machine is locked. Okay. So suppose I have a normal workflow and your system follows my normal workflow. It says this is how he behaves. That's fine. But suppose my workflow changes, and then I get locked. So then what happens at that point then? So I log back in, I put my password back in, and does it learn from that okay, this workflow is slightly changed, this is a new workflow?
Yeah, that's a very good question. We have two approaches, but one of them is that we retrain the model from time to time to learn new behaviors of the person, because, well, imagine that because you install a new application, and then what's happened if you have trained the model without this application, and then you do something like that. So because of that, we are training periodically the model, and we are able to adapt to little changes in the behavior of the person. That's one of the approaches that we are considering right now.
Okay, so my second question is in relation to smartphones. So if you install a service like this on a smartphone, I just wondering what particularly for the two popular platforms, iOS and Android, what are the system-wide permissions needed to do that? Because I think certainly from iOS point of view, if you install a service like this, it probably will not get approval in the App Store. What's your approach to that? Because this is kind of monitoring what users do across all applications.
Yeah. Well, right now we have created a prototype for Android, and the kind of permission that we request is the sensors data and the application statistics. This is something that, because I didn't have enough time to comment into details what kind of data we are getting from the application, but actually we are not getting sensitive data. We are just getting a statistic information. We are not getting, real data from user. This is a mandatory aspect that we consider from the beginning of our approach. And this is something that right now is working as a prototype and a proof of concept. And the permission that we request is the sensor data and statistics information, information from the application point of view.
Okay, thank you. Very good.
No problem. Thank you.
Okay, guys, we're just tight on time, so we might just move over to Sergio. Thanks very much for that, Alberto. Sergio, if you want to share your screen.
Yeah, sure. Just a moment. Application. Okay. See the presentation?
Yeah, that's perfect.
Okay, perfect. So I'm Sergio Lopez. I'm a second-year PhD student under the supervision of Alberto, and I'm going to organize this presentation in two parts. The first one is to introduce the work we've been doing, reviewing the state of the art on BCI concerning cybersecurity. In this work, we detected new future challenges that introduce the second part of the presentation, which is how we are developing neuronal cyberattacks to affect the neural behavior. So, focusing on the review of the state of the art, we identified in the literature different families or different classifications of type of BCIs. So we will focus in this presentation in the first one, which is the level of invasiveness. In the figure, we can see that this classification is composed by three families, which is invasive, partial invasive, and non-invasive. And we detected three main risks. And in the radar plot, we can see four different dimensions, which are integrity, confidentiality, and so on. So our idea was to analyze for each family and each risk in these four dimensions, which ones are which have the highest impact. So for that, we measured that impact in a scale between 0 and 3, being 0 low risk and 3 the highest risk possible. So these four dimensions are integrity, which means the protection of private data in a way that it cannot be modified or manipulated during a communication. Confidentiality refers to the protection of the data to only be accessed by authorized users. Availability is to guarantee that services or applications are available, are ready to use when they are required. And finally, safety, which is one of the most important, because we are working with the brain of the people. So we need to ensure that these devices offer preserve the physical integrity of users. So after this analysis of classifications, we saw that there were a lot of different works that define different functioning cycles of BCI. So our contribution in this work was to unify them in a global vision, doing a differentiation between neural data acquisition and how these BCIs work for neural stimulation. So focusing on the first figure, we can see that the brain gets external stimuli, and with this stimuli, it generates a neural activity. So we will focus in a use case in which the user is thinking that he wants to move a robotic arm to the right, for example. So that user intention is transmitted to the BCI, it's acquired, and those brain signals need to be processed in phase number 3, because we need to amplify the signal, remove the noise, and finally do a conversion from analog to digital signals. That signals are decoded in phase number 4 using machine learning algorithms, because as I mentioned, the user has an intention to perform a task. So this is the moment when the system needs to extract exactly which is the intention desired. And with that intention decoded, the intention is sent to the application to perform the task. And finally, we can send a feedback, an optional feedback to the user to define a closed loop approach. Focusing on neural stimulation, the workflow is counterclockwise because we start in the application. The doctor or even the user defines the stimulation parameters. So, stimulation action. This action is decomposed in phase number 4 to define different firing patterns. And those patterns to stimulate the neurons are in phase number 3 converted to indicate the stimulation specific parameters for the process. So, for example, the voltages of each single neuron or the time separation between those spikes. And finally, in the stage number 2, the BCI performs the stimulation. So why it's important to analyze this cycle? Because our approach was to analyze the functioning of the cycle to detect attacks and countermeasures to fight against these attacks. So that's what we did in this revision. This huge figure indicates in the central column the different attacks that we detected. Well, those with a reference are those detected in the state of the art, and those without a number are our contribution. In the first column, we have the impacts associated with those attacks, each one with a color to perform a map. And we can see, I don't know if you can see the mouse. Here you have a little icon representing the cycle, and in which each one of the stages we indicate a color blue or red, indicating that blue is something, an impact that we detected. It's our contribution, and those in red are detected in the state of the art. And finally, the last column is refers to the countermeasures detected to fight against these attacks. Because this image contains a lot of information, we will simplify to focus only on one single attack. User adversarial attacks aim to present malicious stimuli to users to, for example, we can see in the confidentiality box, to obtain sensitive information. So it's well known in the BCI cybersecurity world that when you present, for example, an image or a sound to the user, the neural activity, it's different when you present a known stimuli compared to those stimuli that you don't know. So based on that, we can get sensitive information of the users, and also we can disrupt the normal functioning. For example, you are trying to do a task and someone plays a sound or show you an image. So everything can be disrupted and consider a sensitive information such as the clinical one. So that would be catastrophic. And finally, to fight against these attacks, there have been 2 countermeasures in the literature, which are training sessions and serious game, which aim to teach users the risk that these technologies can have. And finally, we as our contribution, we define external monitoring system as a solution to monitor everything that it's going on around the user, everything that he's seeing or hearing, to detect that if there is an attack going on. So after this cycle and after this work in general, we detected 4 main challenges. The first one is that BCI devices are not compatible between them because they lack standards. They have not been defined using well-known standards, and they are manufactured specifically to solve specific problems. So they are not quite generic. In addition, we detected that they are not extensible in the way that you cannot include new capabilities, and that concerns cybersecurity, because if we are not able to put on top of all those protocols, cybersecurity protocols, it's a difficult situation. In addition, there is no privacy management in terms that the user cannot define which profiles concerning its privacy he can define, and also it doesn't include privacy regulations such as complying with the GDPR, for example. And finally, and the most important in this presentation, the previous image I presented to you was only focused to data acquisition, not neurostimulation. Why? Because in the literature, there's no related work of cybersecurity or neurostimulation. So we detected a great opportunity to continue my thesis, my research, focusing on how a neurostimulation device can be vulnerable and taking advantage of those vulnerabilities to perform neuronal attacks. So in this link, you have the preprint of this survey we created, if you are interested. And finally, moving to the second part of the presentation, I'm going to explain a little what we are currently doing. So we define a motivating case based on Neuralink. Neuralink is a company and a prototype created by Elon Musk, the founder of PayPal and Tesla and a lot of different companies. So what we detected in this prototype that they presented is that these scenarios are potentially vulnerable. Focusing on the image, you have different implants in your brain. They are connected with wires to an implanted coil under the ear. It communicates wirelessly with a pod, which is a constrained device, like an IoT device, placed under your ear and on the skin, so it's not implantable. And finally, this pod communicates via Bluetooth to a smartphone, and the smartphone is the device that contains all the logic. So, for example, you can program how the stimulation works, and you can update the firmware of the pod, the cybersecurity, and everything. So you can see here the problem, and it is that smartphones are vulnerable. We can think about malware attacks, for example, and the pod is a constrained device, so all the limitations are threats that IoT devices can have. They also apply to the pod. So considering the objectives, in this paper, we want to focus on overstimulation attacks. And for that, we want to implement two well-known cyber attacks from computer science world, which are port scanning and flooding. Specifically for this context, port scanning is based on attacking one neuron per unit of time, while flooding consists in attacking multiple neurons. And after the implementation of these attacks, we want to analyze the impact that they can have over neuronal activity. So what we are doing right now, or what we've done so far, is we have implemented these two attacks focused on overstimulation in a neuronal simulation called Brian2. We have focused our work in the visual cortex using, taking into account a use case based on a mouse trying to exit a maze. And right now, what we are doing is analyzing the results that we got based on those experiments and those simulations. And finally, what we want to do in the future is, as we are focusing only in overstimulation attacks, we also want to work with inhibition behaviors. We also want to try different types of neurons across different regions of the brain. And finally, we consider that it's really interesting to perform the attacks and see how everything behaves on simulated brains, but it's more important to be able to detect those attacks, both the attacks that we define and those that can come in the future. So we need the capabilities to adapt to new challenges in the future. So this is a quick overview of the work that we have done and we are doing these days. So thank you so much for your attention, and any one of you have any question?